Yes. When it stays plugged in, now that I have to sleep.
Okay. All right, guys, are we ready to get moving? It's a little bit of a lot. But never fear, we will hit it again next week with just adding different things. So it'll feel very familiar the second go around next week. So don't feel overwhelmed, okay? We'll get there. Mason, sounds okay? All right. Okay, so as I said last time, I want to give you sort of an idea of what the lecture looks like before we get moving, and hopefully come back to this to keep us grounded. So my idea for today's lecture is going to be to teach you a new model called an autoregressive moving average model. We're going to focus with an autoregressive moving average model 1-1. We're going to start with the definition. We'll look at simulated ARMA 1-1 process. When we're looking at that simulated ARMA 1-1 process, we're going to figure out how to choose the orders for P and Q. We're also, and to be able to choose those orders of P and Q, we're going to learn about extended sample ACF, scan, and then a nice little process in JUMP called ARIMA model group. We'll also, to be able to work with the ARIMA model group, we'll look a little bit deeper into the idea of selecting a model based on information-based criteria, AIC and SBC, which you've seen previously in a regression course, probably. So we'll talk a little about that with regards to time series. Then from there, which is what I believe is sort of a lot, about almost 40 slides, we'll move into a real-world example, and that's case study 9 about, and I've already forgotten what the topic of that one, unemployment, about unemployment. And for case study 9, we're going to just take a quick look at the image and then take a break, and then come back knowing the information from before break, figure out if we can come up with the tentative model using these 3 techniques. And once we have come up with a list of tentative models, fit them and decide which one are we going to go with and why. Once we come up with a couple of options, we're going to examine those then for outliers and level shifts. Okay, so that's what today's lecture looks like. And we'll come back to the slides to keep ourselves grounded. All right. Let's make this as big as possible. Okay, so this is topic 4 in the lecture, in the course, and it's called autoregressive moving average models. As always with our models, we've learned so far an autoregressive model, we've learned a moving average model, and now we're going to look at an autoregressive moving average model. The idea is, I hope what you think it is, where we're putting the 2 pieces of information we've learned previously together and seeing how it applies in the scenarios we've seen before. So the idea here for an ARMA, that's my shorthand, for an autoregressive moving average model, is our hope is we're going to look at our current value of y and use it to be modeled as a linear function of earlier values of y and earlier values of a, which is our white noise. So that idea of using modeling it as a linear function of earlier values of y should sound familiar. That comes from the autoregressive world. Earlier values of white noise comes from what we looked at last week, the moving average world. So now we're putting them together. And so putting them together, we come up with a mathematical formula for an autoregressive model. We're going to start with the autoregressive model of order 1-1. The first one stands for P, and the second, well, they're both ones. The first number stands for P, and the second number stands for Q. P comes from the autoregressive world. Q comes from the moving average. So if you take a look at the mathematical definition, you'll see that what it looks like is a compilation of autoregressive and moving average together. So here, our yt minus mu is equal to phi1 times yt minus 1, yt to the t minus 1 minus mu, plus at minus theta 1 times at minus 1. Here, the mu is the mean at y at each time point, and the errors are the white noise that we expect where they're uncorrelated with each other, have a mean 0, constant variance. If we're going to try to take our model to the next level for prediction intervals, we should assume that those errors are normally distributed. So we're going to need to look at that. So to talk about some of the properties of an autoregressive moving average model, let's start with the world of stationarity. Okay, so for an ARMA 1-1 model to be stationary, we're going to have to require that the autoregressive part of the model be stationary. And we saw that back in topic 2, where if you're having an autoregressive model of order 1, for it to be stationary, theta 1, phi 1 needs to be between -1 and +1. Because something I needed to note before we move to the next slide is that you can rewrite that original mathematical equation where we move the autoregressive part to the left and keep the moving average part on the right. So equation 2, all that I've done here is literally move what I look at as the autoregressive part to the left-hand side. Okay. So we looked at stationarity. So for stationarity, we have to require the autoregressive part to be stationary. For an ARMA 1-1 model to be invertible, we're going to have to require the MA part to be invertible, and the requirement from last week is that theta 1 needs to be between -1 and +1. So the first 5 or so slides, a little, heavy on the math, but not that much stuff. All right, so what we're going to do here is introduce backshift operator. I feel like I mentioned backshift operator before because we saw it as a title in JUMP. So I mentioned it, but we never really said what's the real definition. We just said this is the way of representing a difference in JUMP. So here's the real definition for a backshift operator. And when we move into the future topics, it's much easier to deal with the mathematics when you're using this idea of a backshift function. So if we start with our ARMA 1-1 model, the basic equation 1, rewriting it with equation 2, where you move the autoregressive part to the left, the backshift operator definition is that B of ZT is equal to Z of T minus 1. Okay? So what we're going to do with this definition of a backshift operator called B is rewrite equation 2 in terms of a backshift operator. In my mind, I think it's a little easier to move from the end to back to the beginning. So if you're having a hard time following where this backshift function operator, how it works, is I think it's easiest if you look here at the right-hand side of this left-hand side equation. So if you look at this right-hand side, and if you move to the left, I think you can see a little more clear that we can rewrite this relationship of yt minus 1 in terms of its backshift operator. So write it in terms of B of yt. Okay? So rewriting the yt minus 1 in terms of its backshift operator. So here to the left, moving this direction, we have our B of yt minus mu. And then moving to the next left, I'm sorry, I'm working right to left, which is opposite of how we normally work. All you're doing here is you're pulling out the distributive property backwards, right? You're pulling out the 1 minus phi of 1b. Okay, so this is how the left-hand side in equation 3 comes about. The right-hand side of equation 3 comes about if you look at equation 2, the white noise part. All you have to do is recognize that A of t minus 1 can be rewritten in its using the backshift operator B of at. And so B of at, using that idea, we can rewrite the right-hand side, the moving average part, in this form. Okay. So we're going to use backshift operators, as I said, in the topics to come. So just wanted to introduce it here, okay? Because we'll revisit it again. We'll go through this again to remind you, but just to warm us up. So we've talked about stationarity. We've talked about invertibility of an ARMA 1-1 model. Let's talk a little bit about the correlation of an ARMA 1-1 model. So for the correlation of an ARMA 1-1 model, the correlation between yt and yt minus 1 is equal to this formula. And the correlation between yt and yt minus k is equal to phi of 1 times the correlation of k minus 1 for k is greater than or equal to 2. If you look at these two, I'm going to call them, they're not definitions, they're derivations. And I know I forgot to post that last time. So I have the derivations, but it's long and drawn out. So I will remember this time to post the derivations for this correlation. We're going to use this idea, so we're going to call it a definition for the moment, for the correlation of the relationship between lags, to then move into this idea of talking about what would we expect to see if we were looking at the autocorrelation function or the partial autocorrelation function for an ARMA 1-1 model. So what I would hope that you would see is that if you're looking at the autocorrelation function for an ARMA 1-1 model, that it should decay exponentially or possibly damp sinusoidal, or another thing that you might see in the real world is where the tails just kind of fall off, okay? The partial autocorrelation function should decay exponentially or be damp sinusoidal, or similarly where the tails fall off. And these, what we expect to see, come directly from this idea of those two previous formulas. Okay. So now that we've set up the idea of mathematically of an ARMA 1-1 model, let's go and take a look at some simulated data. So using SAS, oh, I did want to say something about SAS. So I had a couple of, maybe 2 students reach out to me over the past week with issues in SAS. I do believe you take some type of programming course in your master's program. And so I hope you probably encountered many, many times in your programming course that one typo, one difference in syntax can completely cause SAS to like not work, crash, look crazy, give you crazy errors. And I think that's what at least 2 of the students that reached out to me ended up having. It was just a typo kind of situation. I'm still having issues with getting into SAS, but what I do have at my disposal is my code written in SAS. And so maybe and that's sort of how I work in the real world. I use my old codes and I just edit them for my new data sets, that type of thing. And so I will try to post, I'll try to go back through all the topics and post the SAS code so that at least maybe you'll have a starting point. You'll definitely have to edit where the data came from, that kind of thing. But it'll give you a starting point where maybe it'll lead to less typos and then a little less struggle to get some of the analyses done. Okay, so I will, moving forward, try to post a version of the code so you'll have somewhere to start with the typing. Okay, so here is the SAS program for simulating an ARMA 1-1 model. And so this ARMA 1-1 model, if you just pay attention to it, the mu is going to be 0. Okay, so what you end up with here is just yt is equal to phi of 1 times yt minus 1 plus white noise at time t minus theta 1 times white noise at time t minus 1. Okay, that's when the mu is equal to 0. The phi of 1 that we're interested in here that we're going to use is 0.8, and the theta 1 is negative 0.8, and both of those meet the requirements of being between negative 1 and positive 1. So let's take a look. This is 1,000 observations from this simulated ARMA 1-1 model. Let's take a look at what this time series looks like. So looking at this time series, this is what it appears to look like, the 1,000 observations. And what I would like for you to pay attention to is the autocorrelation function and the partial autocorrelation function, right? So what you would expect to see, and we do see, with an ARMA 1-1 model is the idea of our autocorrelation function exponentially decaying, and here for our partial autocorrelation function having this idea of a damp sinusoidal image. Okay, so this is our time series we're dealing with, simulated 1,000 points of an ARMA 1-1. Once we have our simulated data, what we've done in the past and what we'll do here is try to model it with an ARMA 1-1. So using modeling our data set with an ARMA 1-1 using the ARIMA specification little box and filling in a P, autoregressive order of 1, and Q, the moving average order of 1, and then estimating. When you estimate, these are the results you end up with. Things to note, right? Pay attention to your parameter estimates. The parameter estimates for phi 1 and for theta 1. You would like for those to be significant, and they are close to what we simulated. We simulated 0.8 for the phi 1. We simulated negative 0.8 for the theta 1, and they're fairly close here. So those are the things you should take note of. Other things to look at is, we'll go deeper, but it's just a quick peek. You can see a quick peek of the residual autocorrelation function and the residual partial autocorrelation function, and you'll see that it does seem to stay around 0. Not the best image. We get a better image on the next slide of the residuals from jump. When you look at the residuals from jump, what you're able to see is it does appear that the means of the residuals appears to be about 0. There does appear to be a constant variance, and the autocorrelation function here are all within the 2 standard error bars. So what I'm taking away from this, these results is that the ARMA 1.1 appears to have a good fit. The residuals appear to look like white noise. Okay. So, talking about what we've seen in the past. In the past, when we last week looked at a moving average model, what did we see? We saw for a moving average model that the autocorrelation function cut off after lag Q, right? For an autoregressive model 2 weeks ago, we were able to see that the partial autocorrelation function would cut off at lag P, okay? So partial autocorrelation function gives you information about the autoregressive part. Autocorrelation function gives you information about the moving average part. So for an ARMA PQ, though, neither function is giving us, it seems to be, information on P and Q, right? They're both going to be damped, they're both going to be exponentially decaying, or they're going to have this damp sinusoidal look. So how are we going to proceed when there are no obvious cutoffs, right? So that's where we're going today. Just to show you the general definition of an ARMA. So an ARMA PQ, this is the general, no, I did not say that properly. The autoregressive model of order, we're back at the definition, sorry. To talk about the autocorrelation function, oh, I was jumping ahead. So we were talking about not being able to determine where the cutoffs are for P and Q from the autocorrelation function and the partial autocorrelation function. So where do we go from there? First idea is we can look at removing the AR part, the autoregressive part, from Y, and then looking at the autocorrelation function of the resulting series with the hope that it's going to provide us information on the order of the MA process. And how do you go about removing the AR part of the process from Y? All you have to do is what we sort of did back at the beginning of the mathematical definition. If we move the autoregressive part to the left-hand side and call that left-hand side Z of T, what we have now done is we have now sort of have a filtered series, okay? And so, if we just look at the filtered series, we want to investigate what the Z of T looks like. So you can use this function in JUMP called, it's just a calculator kind of thing, in JUMP to create this filtered series. So we have our observations YT that we created previously, right? And take those observations YT and create our filtered series where we subtract the mean, subtract out phi1 times YT minus 1 minus mu, knowing that our mu is 0. Okay, so you're able to use YT and create a function so that we can now have our Z of T's. Okay, everybody, okay, we're coming up, we're creating Z of T's with the hope to see, are we now looking at a moving average process? Because if you think about the equation, the right-hand side is a moving average process. So if we just say the left equals a moving average process, we would hope to see that in the diagnostics. And so if you examine the diagnostics for our Z of T, what we're able to see is that the autocorrelation function does appear to cut off at lag 1. And then the partial correlation seems to follow a damped sine wave. Okay. So it does appear to look like a moving average of order 1. If we just take a little deeper dive, fit a moving average to these Z of T's, when you fit a moving average to these Z of t's, are we going to get the theta we used originally in the simulation? And if you look at the parameter estimates, from having fitted a moving average to the Z of t's, we end up with a theta 1 that's negative 0.7, and that is significant. So it looks like what we created. So the parameter estimate of theta 1 is good.
So I know that in this instance with this data, we knew it was 0.8, so we just put it in there. But so is it just trial and error to try and zero in?
So this is a walk to lead you to the idea of where we're going.
Okay.
So you're not going to do
You're not
this
going to use this process? Okay.
in the real world, no, unless you knew the background of the model to begin with. So this is just trying to warm us up to this idea of how interconnected in an ARMA model the autoregressive part is to the moving average part. And so we have our moving average that we fitted, so we're examining the residuals from fitting the moving average 1 to our Z of t's, and when you look at the residuals after having fitted the moving average, we see what appears to be residuals that are consistent with white noise. And that consistency can be seen with, looks like a mean of 0, appears to look like a constant variance, at least in this plot. Checking out more closely, the autocorrelations, they all appear to be 0, and you could further back that up with the idea of the Q statistic, which are all non-significant. Okay, so telling us that the residuals do appear to follow or look like white noise. Okay, so that's first idea for this world, and we're calling this sort of an idealistic approach to trying to figure out how to come up or determine sort of P's and Q's for our ARMA model. Another idea of investigating is to ignore the moving average process in our equation 2 and fit an AR1 model to Y. And then we would check the resulting residual process to see if it's consistent with an MA1 process. If you look at the Z of t here, what I mean by why would you check the residual process? Because if you look at the Z of t here, what is Z of t really? Z of t is really a Y of t minus an estimated AR1, right? And that idea of the difference between those two is a residual, right? An observed minus what we would expect to get. So this Z of t is really a residual. So if we check the residual process, we would expect it to be consistent with the right-hand side, a moving average. Okay, so if we take our time series, our YT, our original simulated 1,000 points of data, and specify an AR1 model, so here autoregressive order P is 1, what do we end up with? We end up with an AR1 coefficient that's 0.89, which is statistically significant, significantly higher than the original phi of 1 of 0.8. So we've come up with sort of an issue, right? This is, if you compare 0.89 to 0.8 with the t-test, you'll see that you come up with a t of 6. Okay, so statistically, they're very different numbers. Okay. So this one's not working as well. If we examine the residuals from fitting that AR1 model to the Y of t's, what do we end up with? Well, the autocorrelation seems to cut off at lag 3. Okay, so right here, the autocorrelation function seems to cut off at lag 3, and the partial autocorrelation function seems to be damp sinusoidal. So this information here would lead us to the idea that maybe we're looking at an MA3 process, okay, which is not where we know we started from. So at this point, moving with this realistic approach, we would be looking and investigating whether we're dealing with an ARMA 1-3 model for Y. So we would say maybe we need to investigate that. Okay, so if you move on and fit an ARMA 1-3 model to the data set YT, what you end up with in this image here are autoregressive parameter estimate that's significant, and a moving average 1, moving average at theta 1 that's significant, but then we end up with theta 2 and theta 3 that are not significant, okay? So when you end up with these MA2 and MA3 estimated coefficients that are really small and not statistically significant, that's going to tell us we probably need to drop back down with that moving average part. Drop back down to just a moving average part of 1, all right, which is what we investigated on slide 9. Okay, so this sort of realistic approach leads us here. Okay, so if we look at comparing those two models, investigating a 1-3 and an ARMA 1-3 and investigating an ARMA 1-1, what we're able to see is that the ARMA 1-1 seems to be a better fit to this data set than an ARMA 1-3. That can be seen by a comparison of the Akaiki's information criteria and the Schwartz's Bayesian criteria. We're looking for the one with the smallest information criteria, and that happens to come in the ARMA 1-1 output. Okay. So where do we go from here, right? We tried to wiggle our way around getting this idea of where the P and the Q can come from by manipulating the math and focusing on parts of the mathematical formula. But it has a tendency to lead us astray. So luckily, there are two gentlemen who, Say and Tao, I hope I'm not butchering their names, in 1984 came up with, honestly, two techniques for us to help tentatively come up with a model idea for P and Q in ARMA models. And so Say and Tao in 1984 in the American Statistical Association proposed a technique. The first technique that we're going to talk about is called the extended sample autocorrelation function, or ES, extended sample ACF. And how the extended sample ACF, the derivation of the process is spelled out in the American Statistical Association article. But what it is it's based on an iterated least squares estimate of the autoregressive parameters. So it focuses on the autoregressive parameters and tries to come up with estimators for them that are consistent. The sample autocorrelations for the filtered series, our Z of T, is then going to be called the extended sample autocorrelation function, and it's going to be denoted by R sub J of 1 at lag J. This is when we're dealing with an ARMA 1-1 model. Okay. One thing I want to say about the extended sample autocorrelation function, when it's represented with this R sub J of 1, or in the future R sub J of P, don't get bogged down by the notation. Make sure you can do the application, okay? So don't get bogged down by the notation. The notation's a little, in my mind, a little bit cumbersome, but the application's pretty straightforward. So the idea here is, if your true model is an ARMA 1-1 process, then your extended sample autocorrelation function, R sub J of 1, should cut off after lag 1, and that's when J is equal to 2, 3, etc. When you're looking at the subscripts of the extended sample autocorrelation function, the J is going to denote the order of the ACF of the filtered series, and the Q it's called the P. The P, in here 1, the subscript in the parentheses is going to denote the order of the AR process. Okay, so those are going to be the background pieces of information. Take it to the. I went too far. So that was the idea for an ARMA 1-1. So in ARMA 1-1, you're going to be looking at our extended sample autocorrelation functions, R sub J of 1. For an ARMA PQ, what you're going to be looking at are the extended sample autocorrelation functions of R sub JP, okay? Where J denotes the order of the ACF of the filtered series, and P is going to be the subscript for the AR process. So what are you looking for? What is an R sub J of P, okay? So what is an R sub J of P? You're going to be looking for example, if we were dealing with an ARMA 1-1 model that we have been, you're going to be looking for an R sub 2-1 that's going to be close to 0. The idea here is we expect that the value of the autocorrelation function at lag 2 of the series filtered by consistent AR1 estimates to be close to 0. Similarly, for an ARMA 4-2, if we call the extended sample correlation R sub 3 of 4, it should be close to 0 when the value of the ACF at lag 3 of the series filtered by consistent AR4 estimates is close to 0. And you're like, okay, what is that going to do? What does that look like? Well, here are the images of a couple of tables provided by SAS Help Guide. So from the SAS Help Guide for the extended sample autocorrelation function, the first is the exact idea of what the table looks like, okay? So across the top, you have the orders of across the first row, I guess, you have the orders of the MA part of the model. Down the first column, you have the orders of the autoregressive part of the model. And within here, we're looking at this extended sample autocorrelation function statistics. So in one table, when you ask SAS to give you these extended autocorrelation functions, they're going to give you two tables. The first table is going to be of the statistic. The second table is going to be of the probabilities of those statistics. And so what you're looking for specifically is in that second table, those probabilities. So what we're looking for is when our extended sample autocorrelation function is close to 0. That's the part we're looking for. And so we're going to look for the first opportunity where we get a triangle of insignificant values. That vertex is going to be the starting point of our extended sample autocorrelation function of where we're going with our P's and our Q's. So here, in general, for an ARMA PQ, we expect to see a triangle of zeros with a vertex at PQ. So here, it's a right triangle. We're looking for the vertex of a right triangle of, it's not zeros, insignificant p-values, okay? So we're looking for a right triangle of insignificant p-values. And so here, represented in the SAS Help Guide, they represent it with zeros. And so this is a right triangle. If you look here, this is if you sort of say my hypotenuse, okay? And then going over, I can form this right triangle. And so this is telling me that the model I examined should follow an AR1, 2. Okay? It should follow an AR1, 2. The R that the extended sample autocorrelation notation-wise that I'm looking at is R sub 3,1. Okay, so this whole idea of the notation for the extended sample autocorrelation function, the R's, don't get bogged down there, okay? Go to the probability table. That's where you're really looking for. You're looking for the vertex of the right triangles. There will be, in reality, when you're doing real data, more than one right triangle of non-significant values. So that's going to then guide us to tentative models to then further examine.
So then you would just look at each of those and say which one has the lowest AIC?
That's one way, yes. You look at a couple other things. We got to check that the residuals match, but we'll get there. We got to check that the residuals meet our assumptions of white noise, and they don't always. Okay. So you can have, as I said, this output came from SAS, the help guide. So, and there's the address. So we can ask SAS to calculate the extended sample autocorrelation functions for us. And here, all you have to do is in your identify statement to add extended sample autocorrelation function. The default is 0 to 5. P 0 to 5, Q's 0 to 5. So that's the default. You can extend those if you want it to be larger than that. So the output from doing the extended sample autocorrelation looks like this. Okay. So the important part, what we're really looking at, this is the table, the first table you get of the extended sample autocorrelation function. So these are our R sub JPs. The second table are the probabilities associated with those extended sample autocorrelation functions. And as I said, we're looking for right triangles of non-significant values. We're looking for the vertex of these right triangles. So here, when you're looking at the output for these probabilities, the vertex for the right triangle I see would correspond with an ARMA 1, 1. This is my vertex. If you go out, you can see, I went too far, sorry. Let's do the hypotenuse first. So we see if we go here, I can make a small one, all non-significant values, we could go even larger. Still non-significant values. Okay, you could go all the way. All of these. So the model that this extended sample autocorrelation function analysis leads me to say, let's investigate, would be an ARMA 1-1 model. Okay, so you look at the vertex of this right triangle of non-significant values. If you wanted to know what the R notation for this would be R2 sub 1. Okay, that's what I'd say on the next slide. So on the next slide, I just said, where are we going? This gives us the idea, looking at the probabilities of the extended sample autocorrelation function, give us this idea that we need to investigate an ARMA 1-1. You might say, why does it say P plus D? The derivation that Sal, I forgot the first gentleman's name, the derivation from the journal article on the extended sample autocorrelation comes out to be, from this extended sample autocorrelation probability, you end up with a P plus D as your resulting model to investigate. And we'll talk about in the next topics to come how to determine what's the D part of the P. Okay, but from this point, we're just looking at it as, this is guiding us to look at an ARMA 1-1. Okay, so that was the first technique for us coming up with what P and Q to investigate. The second technique by the same gentleman, proposed the next year, 1985, in Biometrica, is called SCAN, which stands for the smallest canonical correlation. So the smallest canonical correlation is a method that's based on an analysis of the eigenvalues of the correlation matrix of the ARMA process. Basically, they're looking for eigenvalues that are significantly different from 0. Those eigenvalues, the percentiles for a scan statistic are less than the probabilities of a chi-square, and so they take their eigenvalues and compare them, they take their scan statistic and compare it to a chi-square 1 degree of freedom probability. And so for the scan statistic, what you're looking for is if you have an ARMA with an order PQ, you're going to identify it by finding the top left-hand corner of the rectangular pattern in which the scan statistics are insignificant. Similar to the extended sample autocorrelation function, there might be more than one pair of values that produce that triangle. So here there might be more than one pair of values that produce a rectangular pattern. And so we'll move forward. When we move forward, we're going to be looking for parsimony and the number of insignificant items in the rectangular pattern to help us determine the model order. So if you look at, this is the output from a scan statistic. This is from a SAS help guide. What you'll end up with are the scan statistics in one table, and then the second table will be the probabilities associated with those scan statistics. When you look at the probabilities, what you're looking for is a rectangle of non-significant values. When you find that rectangle that's full of non-significant values, you look at the upper left corner.
Do these two methods ever differ?
Say it again?
Do these two methods ever differ from one another?
Yes, yes, yes. All the time, all right? And I'll tell you when and why, sort of, they differ. So this is the output from running a scan in SAS. Did I give you the code? Not yet, but I can give it to you later. So this is from running a scan in SAS. As I said, the first table gives you the canonical correlation estimates, and then the second table gives you the probabilities. And what you're looking for is a rectangle of non-significant values. So hopefully what you can see here is there is a rectangle. If you start here at 0.5596 and move to the right, I can form a rectangle. Are you okay with that rectangle? Okay. That rectangle would guide me to, I could even go for this entire side, guide me to say, let's investigate an ARMA 1-1, AR1, MA1, upper left corner of that rectangle. Okay, so that's That's what the next slide says. So this scan analysis led us to a tentative model of examining an ARMA 1-1. Okay. It just happened because we used simulated data that our scan process and the extended sample autocorrelation function led us to the same tentative model to go investigate. That doesn't happen always in the real world. There are a couple of researchers, 3 of them, Stadiniski, Brown, and Werner, in 2008, who did an analysis comparing the extended sample autocorrelation function to the scan technique for determining models selections or identifying models. And what they determined in their analysis is that scans seem to perform better when we're dealing with ARMA models and AR models. Scans seem to perform better with ARMA models and AR models, and the extended autocorrelation functions seem to perform better with moving average models. Okay, so there's just a couple of pieces of information. But luckily, in our world today, 2018, we have software at our disposal. So we're able to perform both of these analyses within seconds, right? So we're not limited by calculations. So we're able to have a plethora of information in front of us for us to move forward in examining. So we also, a student mentioned, we're going to pick the better model because of the AIC or the SBC. Well, how do we know which one to go with, or what's our decision maker? So what I wanted to say about the information criteria-based model selection, it's talked about in your textbook on pages 163 to 164. Hopefully you've also seen discussions on information criteria in other courses, like a regression course. So information criteria is a very, very popular way for selecting your model. The most popular ones or most common ones we see in practice are Akaki's information criterion, which is AIC, or the Bayesian information criterion, or Schwartz's Bayesian criterion, has a couple of names. Depending on what software you're using, you'll see it represented with the letters BIC. Sometimes you'll see it represented with the letters SBC. Okay, so they all stand for the same information criteria. Something you probably saw in your regression course is that the penalty function for a BIC is stronger than that for an AIC. And then the 2 other pieces of information that I hope you were comfortable or knew about depends on what's your goal. What's the goal of your analysis? If your goal is to have a parsimonious model, then SBC Schwartz's is typically preferred over AIC. If parsimony is not the goal of your analysis, but instead you just are interested in minimizing your prediction errors, then you might focus on the AIC over the BIC. Okay. A statement wanted to say, we talked briefly about MAPE and MAE, the mean absolute percentage error and the mean absolute error. In general, they have a potential for overfitting. They generally should not be used to select a model unless they are computed on a validation data set. Because in general, if you choose a model whose errors are smallest in the validation period, you may end up overfitting the data within the validation period as well as in the estimation period. So typically when we're doing time series model selection, most people shy away and don't even look at MAPE and MAE. Okay. So there is a third idea. So we've talked about using extended sample autocorrelation function to help us come up with PQ. We've talked about using scan to help us come up with PQ. There's a third option, and it's based on this idea of sort of the information criteria, is using a software system like JUMP. Specifically, the analysis section in JUMP that you're using is called ARIMA Model Group. Okay, so it's an option on the time series platform with the red triangle menu, and it's going to allow a user to fit a range of ARIMA models by specifying the range of orders fit. So for each model fit, the following statistics are going to be provided. They're going to give you the variance, AIC, SBC, R squared, -2, log likelihood, the MAPE, and the MAE. So by default, the output from the ARIMA model group is going to be ordered by the AIC values. You can change that pretty easily, and I'll show you how to do that if you're interested in looking at the SBC. Okay. So the ARIMA model group in JUMP. This is what it looks like. So the ARIMA model group, what you're going to do here is you're going to give it a range of values to look for. So specifically in this slide, what we're looking at is looking at the autoregressive orders from 0 to 2, the moving average orders from 0 to 2, and then all those combinations. Okay, so what we end up with here, you can see listed, is a total number of models 9. All right, everybody okay with this idea? So we have 3 possibilities for the autoregressive order, 0, 1, and 2, 3 possibilities for a moving average model, giving us a total possible, I always get combination permutation of 9 models that we can examine. And whenever possible, you should try to limit the number of models fit in any application of an ARIMA model group. And why is that? Because the numbers blow up pretty quickly, right? And so when the numbers blow up pretty quickly, one thing is you're having to examine 50 models, 100 models, depending on how wide, how far your range goes out. All right. So looking at the ARIMA model group for 0 to 2 for both the autoregressive order and the moving average order, this is what the output looks like. We ended up with 9 possible models, and you can see they're all listed here, but they're listed in order, as I said, of their AIC, smallest on top in increasing order. And so what you're able to see here is that the ARMA 1.1 model fits our data set better than any of the other models, right? It has the smallest AIC and the smallest SBC. If you look at the SBCs, they're not ranked in order, it just happens that they are in order. Okay.
Can you please comment on the weights?
So the question is, can I comment on the weights? So the weights, I knew someone was going to ask. So the weights, let me find my, because I looked it up, because I was like, what are these weights? Give me 1 second to find my notes. No, I'm not finding them. Okay. So what's in, I'm looking, I wrote it somewhere. Give me just 1 long second. It's a weighting of the AIC, and where did I write those? I didn't. Some of the squares. Oh, I don't know where I put it.
It's okay.
But it's a weighting of the AIC. If it's not on my paper, I have it in my phone because I just looked it up literally right before I walked in. So we're almost at the break. And so as soon as we get back from the break, I guarantee I'll tell you what the weights are. We're not going, it's just, we'll look at it when we come back from the break, guarantee. All right? And so to get us to the break, I wanted to introduce where we're going. So we're going to look at a real world example. What we're going to look at is national unemployment rate from January 1990 through February 2017. And it's an unemployment rate there. And this is where the data came from. And this is what the data looks like. Okay, so this is the change in unemployment rate, monthly unemployment rate. And what I'd like for you to note in this change in monthly unemployment rate is that what do our autocorrelation and our partial autocorrelation functions look like? Well, they look like, hopefully, nothing you've seen before, right? Where would you go, right? What P, what Q might you investigate just from looking at these autocorrelation functions and partial autocorrelation functions? Any suggestions? Any ideas where to go? No. I feel like if 7, I mean, right, you'd like be throwing a number out there. Okay, let me just try it, right? And so you'd be at a moving average of 7. Where we go, I don't know, here, right? So you wouldn't necessarily know, right? So what we're going to do So for the autocorrelation, you might end up with a moving average of 7. For the autoregressive, you might look at, 3, 4, 5, 7 again, but really unsure. So luckily, Xiao and his partner came up with other ways for us to figure out a P and a Q for an ARMA model. So what we're going to do after the break is look at this change in monthly unemployment rate and try to come up with using extended sample autocorrelation function and scan and the model group in JUMP to determine what tentative models we should explore. And once we explore those tentative models, how do we do that? I want to get out of here and come here so we can get back to where we're going. So what we're going to do after the break is look at the models suggested by extended sample autocorrelation function scan and the ARIMA model group and JUMP. Take those tentative suggestions for P's and Q's and fit the models. And then once we have those, it's going to end up being 6 fitted models. We'll look at whether they're valid or parsimonious. And if they are, we'll take a couple and look at the additive outliers and the level shifts. And that's what we're going to do after break. It is 7:54, so let's come back, reconvene at 8:05, and keep moving. And how does this sound? Talk again. Okay. Alrighty. So guys, we're getting back to it. And I had said we would hit on the weights displayed in the model comparison table in JUMP. And so just from the model comparison report, this is the JUMP support documents online. It says that the AIC weights here give normalized AIC values that sum to 1. The AIC weight can be interpreted as the probability that a particular model is the true model, given that one of the fitted models is the true. Therefore, the model with the AIC weight closest to 1 is the better fit. But in general, I just wanted to say that the idea for AIC weights are not what we normally use as our norm for deciding on a model, okay? So that's not a traditional way of looking. So back to where we are, okay. So where we're going, the unemployment rate, monthly unemployment rate data, that's where we're going to investigate. And so what we saw was that the autocorrelation function and the partial autocorrelation function don't give us a clear and definite place to look. It gives us lots of combinations we can investigate, but it doesn't tell us clearly where to go, all right? So what are we going to do? We're going to use Tao's techniques of extended sample autocorrelation function and scan to give us a place to begin investigating. And so in SAS, you can run both of them. They're both options in the identify statement of PROC-ARIMA. And here, as I said previously, the default is 0 to 5 for the P and the Q. And so here we're going to investigate 0 to 6. Okay. No. Okay. Alrighty, so this is the output from the extended sample autocorrelation function and the scan function. Make sure when you're looking at this output that you have your wits about you, right? Because it looks like a matrix of decimals all over the place, easy to get lost. So you have to remind yourself what are you looking for? I have to say, in general, in my mind, the scan function, the scan statistics are easier to see, right? You can jump into a scan table and grab out the upper left-hand corner of the rectangle of insignificant or non-significant values a lot easier sometimes than finding the right triangles on the extended sample autocorrelation function. So let's start with the scan, okay? So for the scan probability, we're looking for a rectangle of non-significant values. And what I hope you would see that there is a rectangle full of non-significant values that starts here at an ARMA 1, 1 with 0.2201, and it makes a full rectangle, and inside of that rectangle is full of non-significant values. So one tentative model to investigate is an ARMA 1, 1 for this unemployment rate data. Everybody okay with one model? There's another model that you can investigate in this scan output, and that model is an ARMA 60 or an AR6. And you can see this rectangle down here. It's a skinny one, but it's there. All completely full of non-significant values. Okay. Everybody okay with the scan? Okay. If we had extended it, there's more non-significance, but this is our upper left corner. All right. So for the extended sample, oh, I have a typo. It's supposed to be extended sample ACF. Okay. For the extended sample ACF, we're looking for right triangles, and we're looking for the vertex of those right triangles. So there are quite a few. So let's take a quick look at them. We're looking for right triangles of non-significant values. So the first one that I see, the right triangle of non-significant values is, we'll start with the first one probably. Here, yeah. So where do you even start, right? So typically the idea is I kind of look across, going left to right, and at the same time coming down. So when you look across and coming down, your mind quickly says, okay, yes, let me go and grab 1, 1. But it's not a full triangle of non-significant values under careful inspection. There is a problem with the ARMA 1, 1, if you see here, with our significant value sitting in that triangle. Okay, so what I mean is you have to have your wits about you. Really, so maybe if you're looking at your output, you use a highlighter or something and check where all the non-significant or the significant values are. You have to be very careful because they can all jumble together. So ARMA 1, 1 is not a model we would look at based on the extended sample autocorrelation function. The first model I think that we would grab would be an ARMA 3, 3. Okay, so if you look at an ARMA 3, 3, that puts us here, and the triangle goes here, over 4, diagonal, down to 4, okay, this kind of idea. I said 3, not 4. So the ARMA 3, 3, so can you get to that spot? Yeah. And then the right triangle formed from the ARMA 3, 3, if I go over 3, diagonal with the 3 squares, and up. Okay, so this is one right triangle, giving me an ARMA 3, 3. There are lots more, okay? There's also an ARMA 4, 3. So here, going diagonal, there's a right triangle formed here. So 4, 3 is a second model we might investigate. Yes, question?
Did you say that ARMA 1, 1 would not count?
It's not going to count. And the issue is there's a significant value sitting in its triangle. That significant value is in this, I don't want to use the R, but so let's look at it with regards to ARMA. I would say an ARMA 2, 5. Do you see that value for ARMA 2, 5? It's significant. Okay, so it's, when you make the right triangle, all elements in the right triangle need to be non-significant. So 1, 1 doesn't pass the test.
Dr. Mhoon?
Yes.
I can make a right triangle using the AR 1, 1, ARMA 1, 1.
Okay.
So go in there, go right 1 box, go right second box, a third. So there's, yeah, so AR 1, 0 through AR 1, 4 would be the top of it. That's 4 boxes. And
yes.
you can go down for you.
I'm assuming, maybe I heard you wrong, but maybe you're making a little right triangle?
Correct.
Yes, a little one. So the traditional default for all softwares and the recommendations from SCAN is you go out 5 or more. Okay, so recognizing 5 or more, you need to use the full data set that you display. So at least say if we lived in the world of 5. Are you okay with that? So you need to at least go out to 5.
Yes, that's the key.
That's the recommendation from Sal.
Do the values inside have to be non-significant?
Non-significant. What makes the triangle and inside of the triangle all need to be non-significant. So that was a good observation. So thank you. I hadn't specified that.
And what do you set for non-significant? 95%?
95%. Anything larger than 0.05. All right. So we've only located 2, correct? We've located 3, 3. We've located 4, 3. There's also one at 5, 3 here. So if you come out and go over, okay, and in the right spot. If we had, I only included up to 6, but if you print out more, you'll see that they're able to make a full rectangle. Recognize what we're doing here. So don't like completely lose your mind. This is the world of exploring. Okay, so we are now looking at our data set and we're trying to fit models to it. So to some extent, fitting a model to it is, you pick one of these and maybe you read the table wrong and you apply it, it's not necessarily going to be the end of the world, because what will probably happen is it's not going to meet one of the assumptions behind the ARMA model. Something like the residuals needing to look like white noise, typically, or if you apply it and you fit it to your data, maybe some of the parameter estimates are not going to be significant. So then you have a clue. So even if you make a mistake in your quick investigation of this extended sample autocorrelation function and say, okay, I'm going to go explore this model, I'm going to go explore this model, and one of them happened to be wrong, I guarantee you when you go to get and look at the assumptions of fitting that model, that it won't make the cut, okay? So don't be like completely afraid to jump into this table. And there is a way to read it, but even if you make a mistake reading it, the next step will clean it up for you, okay? So when you fit the models that you've selected, one of them, it won't fit more than one. And so what we're doing here with this scan and this extended sample autocorrelation is to come up with a list. Come up with a list of models to now fit to our data to see if we are able to represent our time series, okay? So we're making a list. So if there's a mistake in your list, it'll end up getting cleaned in the wash, I guarantee. And so here, I would look at a 4-3. I would also look at a 5-3 down here. You can even go as far as a 6-2, okay? But you have to see more. You can see more of the image. Oh, something else. I'm saying that incorrectly. If you look at the 6, that's true. I'm sorry. If you flip the triangle, you can see that everything in it is non-significant. So for example, 6-2, this is the corner of the right triangle. If you come over to here, let's see, let me get my 6. Here and going up to here, then down, you'll see that everything's non-significant. Same idea for the 5-3. If you flip your triangle, look at it in the other direction, you'll see that it's made up of all non-significant values. Similarly, there's one more you could probably grab out of here, which is a 1-5. And so if you look at it here, this is, let me look at my corner for the 1-5. I used this as my diagonal. If I look at it here, oh, that doesn't look right. Where's my 1-5? My 1-5, oh, this is my corner. Going down and then going up. Oh, I'm sorry. Maybe I shouldn't have grabbed the 1-5. I have to look at my triangles class. I'm very sorry. My 1-5, I did a, I'm not happy with my 1-5. I did a mistake. I think that's a mistake. Because 1-5 grabs some non-significant values. There's no way around it. It's going to always grab some. So I think I have a mistake on the next slide for the 1-5. I'll have to fix that. So, okay, but I looked at the 1-5. Alrighty. Okay, so we have a list. The whole purpose of looking at the extended sample autocorrelation functions and the scan function is to come up with a list of P's and Q's to apply in an ARMA model to our data set, right? Because we couldn't determine it from a partial autocorrelation function or the autocorrelation function. So from this point, we're now going to take that list of tentative P's and Q's and explore them. So we looked at the scan and the extended sample autocorrelation functions up through 6. You can do the same thing in the ARIMA model group, right? So the ARIMA model group option in JUMP allows you to look at a range of values. So we're looking at the range from 0 to 6 for autoregressive and 0 to 6 for moving average. And then you're going to end up with 49 models, right? So with all those combinations, we're going to end up with 49 models. And this is a listing of all 49 of those models. And remember what the ARIMA model group does is it orders them, ranking them with their AIC information, their AKP information criteria, smallest to largest. So the ARIMA model group seems to tell us that based on AIC, that the ARMA 5.2 is the best model to use. Okay. Just a side note, you might be wondering why there's a completely empty column here for MAPE. If you recognize, there's 91 of the values have a value of 0, and so the division for the MAPE doesn't work properly. All right, so hard to make a decision from this idea of AIC being the smallest. You want to say, okay, well, I like AIC or I like SBC, right? Depending on what the goal of my analysis is. So you can use JUMP and manipulate it to come up with the ranks for AIC and the ranks of SBC so that you can side by side compare. AIC says this is the best one and SBC says it's number 8, that kind of idea. So manipulating JUMP, all you have to do is go click anywhere in the table, select columns, then select AIC and AIC rank and SBC rank. Once you've selected AIC rank and SBC rank, this is the output that you will get. And now we're able to more clearly see what's the difference between the information criteria. So for example, that ARMA 5.2 that gave the AIC rank of the first place is really a SBC rank of 9. Okay. If we want to then organize the output by the SBC rank, you can easily go in there and do that by clicking anywhere in the table, telling it to sort by columns, select SBC rank, and click on the box next to ascending, and say OK. And so we're going to now have a table with the SBC ranks ranked from 1 to the largest. And so the SBC rank says that the best model is an ARMA 1.2. Okay. So looking at this output, we're able to locate the SAO's ideas for the models to investigate. And so with the idea for SBC, we're looking for like a parsimonious model. So looking here, this was the first model that was chosen by SCAN. It was an ARMA 1.1, and it has a rank of 6, right? The first model chosen by extended sample autocorrelation function, which was this ARMA 3.3, it has a rank of 12, okay? And further on. All right, so you can further investigate how SCAN and extended sample autocorrelation compare to SBC ranks or AIC ranks, if that's what you're using. Okay. Oh. So if you click, so once you have your output from a ARIMA model group, you want to then look at the fitted model. Easy way to look at the fitted model from this point in JUMP is to just click report and graph, and it will give you the information, the diagnostics connected with that model. So it's pretty quick and easy to do once you have the ARIMA model group report out. So click report and graph next to whichever model you're ready to take a look at. And so here we're looking at the ARMA 1.2. So the ARMA 1.2 was the model with the lowest Schwartz-Bayesian criterion, which is, we're looking for typically for the idea of parsimony. And what I would hope that you take away from this slide is you should investigate the estimates. Make sure that your estimates are significant. And so here, the estimates for the, this is an AR 1.2, for the phi of 1 is significant, and the thetas 1 and 2 are also significant. Question?
Yes, what's the point of doing the scan EC, ACF if we just basically chose a model that wasn't even a part of that?
Oh, we're going to look at those two.
Okay.
Yeah, we're going to look at those two. So the hope is don't just rely on one technique. We have software that's able to do these techniques in seconds. Use all of them to give you a group of models to investigate. Okay, so you want to have an open mind because you will find different results for different data sets. All right. And as you remember, the research done by I think they were Russian, where the extended sample autocorrelation worked best for a moving average, and the scan worked best for ARMAs and ARs. So we get different results depending on what your data looks like. And so this was the ARMA 1-2 fit. This was using the SBC criteria. And so we're looking at the residuals. We're able to see that, oh, I went too far. The residuals appear to have a mean of 0. The ACF remains in the 2 standard error bars. If you look at maybe the Q statistic, you're able to say that the residuals appear to be white noise. This appears to be a valid model, okay, because the white noise assumption of the errors appears to be met. You might take it a step, okay, we're going to move on to the next one. So the model that was chosen by SCAN was an ARMA 1-1, okay, so this was the first model chosen by SCAN. And what you're able to see here for a 1-1, that the phi 1 and the theta 1 parameter estimates are both significant. That's the first thing you'd want to look at. Then you want to go and examine the residuals. Residuals similar to what we saw with the ARMA 1-2 is that the Q statistics, some of the Q statistics are significant. So there appear to be some issues here with stating that the residuals are white noise, right? This here, based on these residual diagnostics, I would say is not a valid model. Our assumption of white noise errors is not being met when we fit an ARMA 1-1 model. This model was recommended by SCAN. Are we okay with this? Mm-hmm. Okay. Moving on, examining another model. We're going to examine a total of 6 models. We're going to look at an ARMA 3-3. This was the model that was chosen by extended sample autocorrelation function. The parameter estimates for this extended sample autocorrelation function, ARMA 3-3, are all significant. That's great. So all of the phis, 1 through 3, and the thetas, 1 through 3, come out as significant. We then take it and look at the residuals. The residuals look good. The Q statistics are all not significant, telling us that they appear to be white noise. Looking at the image of the time versus residual values, it appears that we have a mean of 0, constant variance. This ARMA 3-3 appears to be a valid model. So we now looked at 3 models. We're moving on to the second rank for the SBC, okay, for the Schwarz-Bayesian criterion. This was the second model that it suggested, which was an ARMA 2-1. Looking at the parameter estimates, they are significant, the phi 1 and 2 and the theta 1. So that's giving us an idea that this is parsimonious, that we're able to get parameter estimates that are significant. Take a look at the residuals. The Q statistics, the Leon box Q statistics, not significant. So these residuals appear to be white noise. You take a look here, all the correlations seem to stay tightly within the 2 standard errors, mean of 0, constant variance. So this appears to be a valid model. This was SCAN, this was the second one from the Schwarz-Bayesian criterion. The second lowest. Then taking a look at the second model chosen by SCAN, what we see here is that not all the parameter estimates are significant, right? So this was an ARMA 6-0 that it chose, or an AR6. So if you look at all of the phis, we end up with phi 1 not being significant. Similarly, phi 4, right? So because of this, not all the parameters are significant, so what we're looking at is not a parsimonious model, not one that's going to be easily explainable. Still, take a look at the residuals. The residuals appear to be white noise, right? So the residuals appearing to be white noise lead us to this idea that we might have a valid model.
Okay, yeah, I was just gonna ask, so it's a valid model, but you might not wanna use it?
But you might not want to use it because it's not going to be easily explained, right? It's hard to explain in AR6 where you have fees that don't work, right? So not a parsimonious model, but it is valid. These residuals do appear to be white noise. If you look at the Q statistics, they're all not significant. They stay within the autocorrelations, stay within the 2 standard errors. Image of the residuals appears to be mean of 0 constant variance. I think this might be the last model. So last model, 6th model that we're investigating here is the model chosen second by the extended sample autocorrelation function, which is an ARMA 4.3. And so this ARMA 4.3 shows us that the AR1 parameter estimate, the phi 1 is not significant. So leading me to the idea that this is not going to be a parsimonious model, not going to be easily explained. If we take a look at the residuals for the ARMA 4.3, the residuals appear to be white noise. The Q statistics are all non-significant. The autocorrelation function stays close to 0 inside the 2 standard errors. The image of the residual plots, mean of 0 constant variance, seems to work. All right, so to summarize what we've just done, we investigated 6 models. These 6 models came from different criteria. We looked at the SBC information criteria, we looked at what was suggested by SCAN, and what was suggested by extended sample autocorrelation, at least the top 2. And so what we were able to determine is that an ARMA 1.2 and an ARMA 2.1, both of the, let's say an ARMA 1.2, an ARMA 2.1, and the ARMA 3.3 all appear to have parsimonious models. That means their parameter estimates were all significant, and they appear to be valid, which means their residuals appear to meet the assumption of white noise. Question?
Yeah, I have a question from Donald. He said, can you explain what you were meaning? He said, we have a number of valid models, but I'm unclear how to interpret any of them. That is, if I was describing the output to a business person, how would I describe the output?
Okay.
He asked me if he wants to come over and ask it.
Oh, on the screen.
He just sent it directly to me.
Okay. I think I understand the question. So at this point, what we're trying to, we haven't gotten to the interpretation phase. At this point, we're trying to come up with a way of modeling our real world data. And so the only way where we are at this moment, what we're doing is we're trying to come up with an idea of a model that has valid assumptions. And the main one is that our errors are white noise. And then we're dealing with this idea of parsimony, with parsimony being, if we say we have an AR6 model, then we expect mathematically to see 6 phi coefficients. So they should all be represented in the model. And then we go and look at the output from fitting that, and they're not there. So then that would say, okay, I need to back away from that one because it's not truly an AR6 model in the traditional scheme of things. And so his question was sort of the idea of how I then interpret this to my coworkers or my higher ups, is we're not there yet. We're at the point where literally I just want to pick a model. How do I even know which one to bring to the table, let alone what is it saying to the audience, right? So right now we're still in the world of just picking a model because we haven't picked one. We still have 6 on this page, and so you say, how do you know which one to go to? Well, definitely you want to be able to have valid and parsimonious, right? You want the assumptions to be met, the mathematical assumptions to be met, which is our errors are white noise, and you want it to be parsimonious, where all of the coefficients that are supposed to be in that model are significant. Mason, you have a question coming?
No, I'm just making sure
Okay.
that's what he meant. He
He-
said that, he'll wait for your interpretation.
Okay. All right. And so looking at our summation of what we found from these 6 fitted models, what we're able to see is we have 2 that had non-significant coefficients. So I would remove those from my further investigation, right? Then I would go and look at my white noise error assumptions. Were they met? In one of them, the ARMA 1 was not met. I would then also remove that one from further investigation. Okay, so moving forward from this point, if I was alone at my computer with this in front of me, I would move forward with investigating 3 separate models. Okay, I'd probably investigate ARMA 1.2, ARMA 2.1, and ARMA 3.3. In my slides, we move forward with ARMA 1.2 and ARMA 2.1. Why? Because in the real world, but I live in the math world a lot more than the real world, ARMA 3.3, we're getting to estimating a lot of parameters. The more parameters you estimate, the harder is going to be the interpretation of the data. And so one of the, I think it was back at the first day, keep it simple, stupid kind of statement is you want to, if you have models that seem almost identical with regards to prediction, with regards to even parsimony, you want to go with the ones that are simplest, right? So in comparison, an ARMA 1.2 and an ARMA 2.1 are much more simple to explain just because we have 3 coefficients compared to 6 coefficients, right? So in the real world, I would easily see a researcher just reducing it to these 2 investigations here, and that's what I did moving forward. So what shall we do next? We're going to investigate this ARMA 1.2 and ARMA 2.1 and bring in the idea that you always, we learned last time, should investigate outliers and level shifts to come up with the best model. Okay, alrighty. So this is going to be, what are we doing here? Oh, we're doing an analysis of the ARMA 1.2 model on the unemployment rate data. So we're applying it, and we're going to check for outliers. We're going to look for a maximum of 10 of them with an alpha 0.005. So I also had a few questions over this past week about the alpha level for the outlier investigation. On that homework assignment, it wasn't specified, right? And so I was getting you warmed up for the idea that this is somewhat of an exploratory process. It's how deep are you going to go with your how deep are you going to go? How many outliers are you going to grab? How many models are you going to investigate? So that is going to end up being somewhat of a personal choice based on the world or the industry you live in. How specific, how small do they want the alpha to be, or how large do they want the alpha to be? So it's really a case-by-case decision, a person-by-person decision. And so I know the results from the homework too that are being submitted everyone's answers are going to be different, all right? And so that's what's going to end up happening a lot moving forward, that each group's submission are probably going to vary. In the next homework assignment, I do specify the alpha level, so you're not so out there, because you're already exploring, you'll be exploring different models, because you'll all make maybe different decisions. So this is an application of the ARMA 1.2 to the data set, unemployment rates, and checking for outliers. And what we're able to see here with the outlier detection in SAS, maximum number was 10, and what it located was 7 with an alpha of 0.005. So this ended up being 5 additive outliers and 2 level shifts. Once you see you have these 5 additive outliers and 2 level shifts, then we rework our model, including regressors for these dummy variables, doing the iterative process of also still checking to see if there are any other outliers once this new model is fit. So this is SAS code for rerunning the model, adding in the 5 additive outliers and the 2 level shifts. When you do that, what you end up with here is an outlier detection summary that says there are no more outliers detected. When you check the estimates for the parameters, you'll see that they are all significant. Okay, So we're happy with and when I say they're also irrespective of the mu, okay? So I keep looking at the coefficients and not talking about the mu. The significance should be in your phis and your thetas, okay? So that's what I'm talking about, the significance. So this looks good. So this is the output for the model that includes regressors for the additive outliers and level shifts. The right-hand tables is the representative of the model when you did not account for outliers in the data, okay? And what you can see when you compare the two is that the AIC and the SBC both are lowest in the model that takes into account regressors for the additive outliers and level shifts. Okay. So that's the model I'd move forward with. You need to check its residuals. All right. So when you check the residuals on the model, including regressors for the additive outliers and level shifts, the autocorrelation function looks good, as well as the white noise probabilities are all fairly insignificant. Take a little deeper look at the quantile plot for the residuals. What you see here is that the residuals are fairly normal, and I think I got one comment over the week about the normality of the residuals. So, you know, there is always a little bit of wiggle room with regards to how visually inspecting a quantile plot for normality. I have a tendency to look between -2 and 2, okay? If it's looking fairly good between -2 and 2, I have a tendency to move forward. If it's not, and I'm also keeping an eye on those ends, and it just doesn't look ridiculous, right? It's just 1 or 2 residuals floating around. You know, you don't want 10, you know, or 12 crazy points at the ends, and you say, oh, it's really not looking normal. But I have a tendency to zone in on -2 to 2 to check for normality and just sort of eyeball the ends to make sure it's just not completely crazy looking. So here, I would say that these residuals are fairly normal. If you want it to be more, you want a mathematical number, a statistic to check for that normality of the residuals, you could move further and do a statistic like Anderson-Darling. That's probably the one I might try to check. If you wanted to be able to show someone, see, this is the statistic and the null hypothesis is here. So instead of just visually inspecting a quantile plot, you could go and do an Anderson-Darling, you could do a Klommer-Smirnov, you could do a Shapiro-Wilks. But I have to say, in general, Anderson-Darling is probably the more popular one for checking for normality of residuals, time series data. Okay, so this ARMA 1-2, including regressors for the additive outliers and level shifts, looks pretty good. All right, so let's investigate the ARMA 2-1. That was our other model. There was a third, the ARMA 3-3, but we're not, you know, too many estimators. So we're going to investigate the ARMA 2-1 model. Same SAS code. We're going to investigate a maximum of 10 outliers, alpha 0.005. And when you run that code, you find that yes, with a maximum of 10, there comes out to be 7 outliers detected. Same 5 additive outliers and 2 level shifts that we found in the previous fit of an ARMA 1-2. So both of these models have pinpointed or pointed out the same outliers and level shifts. So now that we have these outliers, significant outliers and level shifts, include them in the model, this ARMA 2-1. So rerunning the code, creating the dummy variables, and including the regressors for those additive outliers and level shifts. This is that code doing the iterative process of looking at outliers. What we come out with this analysis, similar to what we saw before. When we check for outliers, now that we've applied the regressors for outliers and level shifts, there are no more outliers detected at this 0.005. And looking at the estimates for the parameter estimates, they are all significant. Okay, so this model looks good at this point. We still need to check the residuals. Okay, so taking a look at the residuals, we're able to see that the residuals do appear to be white noise. The autocorrelation function falls within the 2 standard errors. The white noise probabilities are all insignificant. Similarly, if we're going to move forward with prediction, taking a look at the QQ plot between -2 and 2, it looks fairly normal. And so here, I'd say that the residuals do appear to be fairly normal between -2 and 2, and that this model appears to work as well as the other when it comes to meeting the assumptions. Okay, so which one do we go for, right? They have the same number of coefficients. Their residuals both appear to be white noise, right? So how do you pick one? So if you have to pick one, the decision is we only can use one model, then at this point, when you're down to something like 2, I would go with the lower value for SBC or AIC if that's what you were using as your decision maker. But we've been using SBC. So the lower value of SBC, and the one with the lower value of SBC ends up being the ARMA 1-2 model here on the left, -373. Oh, I said that wrong. Yeah, -373 compared to -372, right? But the difference between these information criteria are very, very small. Okay, and both models identify the same additive outliers and level shifts. But if you had to pick one, you would possibly pick an ARMA 1-2 based off the lower value of the SBC. Okay.
Dr. Mhoon,
Yes.
I thought we agreed it was the absolute value of the information criteria.
I know that was going to come back to haunt me. Did I ever I never made an announcement, huh?
Yeah, there was an email.
I thought I sent an email. So soon after that class, I corrected myself and said it is the smallest value. I knew that was going to come back to haunt me. I thought I'd send an email / an announcement soon after. Okay, so I am sorry that you were still holding that misinformation. Okay?
Thank you.
You're welcome. All right, so let's take a look at the predictions of the forecast. So if we're still in this world, if I'm going to look at both of them, right? I'm open. I don't have to choose one. Let me examine what's going on with the forecast. So if you look at forecasting observations 329 through 332, you'll see that with the actual values being listed here, okay? So these are change in unemployment rates, and these are our forecasts. What you're able to see is that the truth does lie within the 95% confidence limits that are provided. Okay, it's not the best, but it's okay, right? So they lie within the confidence limits. This is for an ARMA 1-2. For the other model, the ARMA 2-1, you'll see the forecasts for 329, observations 329 through 332. Similarly, the truth lies within their confidence intervals. The take-home message from the ARMA 1-2, the ARMA 2-1, is that the performance of these two models are very, very similar, right? Are very, very similar. So if you just had to pick, go with the lower AIC, the lower SBC.
Oh, Dr. Mhoon,
Yes.
so you don't do the 30% holdout in these kind of models? So you
To do like a validation and,
Yeah.
oh, yes, we'll get, so this, yes, you can, in the real world, yes, I would do a validation and a training set, but we're just working with all of it at the moment. Okay, are there any questions? I know it's a little bit of a lot. So where we're going, there is, and so I wanted to do a discussion. There is an exercise, and in that exercise, it is examining a data set, looking at the extended sample autocorrelation function, the SCAN, and the JUMP program to come up with a list of models to try to fit to a data set. Once you narrow it down based on validity and parsimony, then take it further and investigate the things like the additive outliers and level shifts. My question, looking at the future, is next week we're going to move into ARIMA, which is very, very similar to what we've done today, just adding the idea of differencing back in. Okay, so it's a reiteration of this, adding in differencing, but there will be a test coming up 2 weeks from today. Right, and so I guess my feeling about the homework assignment, I do want it completed, but my question is, do I say 1 week or do I say 2 weeks? I don't know. I'm open, but it's, you tell me. Or is it wrong to ask? Are there any opinions? Does anyone care?
More time's better time.
Yes, but then it bumps into studying for the test. So,
I think the 1 week's better because it'll be like last summer when we were doing group projects, studying for a test at the same
so
time.
let me just say this. So Javier controls my due date submissions. He's the one who programs them. I'm going to put it as due next week before class. If your group wants more time, email me. Okay? And I'm open to your group having more time. Yes.
So the exam is in 3 weeks, right?
It's a ninth.
It's the 9th.
Oh, okay. It's the 9th.
It says so on the syllabus. You can change it.
We're going with the syllabus. I've been going in my mind that it was the 2nd. Okay. Then we're fine. Okay, great. Then you have more time. Then yes.
So do the 2nd?
Yeah. No. Do it for the 25th so we can
Okay.
keep moving. I thought I even opened a syllabus. Maybe I closed it since. I really thought it was.
So with that,
The
does that mean
second,
we're only
second.
covering material in the test up to the 26th?
Possibly. Yes. Yes.
Sounds good.
Yes. But I might go. So I was only doing half of topic 5, but I'm going to do probably all of it. So, but yes.
Can you do a Riemann model to figure out when we're testing?
I'm trusting that you all know the calendar, but I didn't go back and look at. I just kept saying it was the 2nd in my mind. But okay, if it's the 9th, it's the 9th. It's whatever the syllabus says. I'm perfectly fine with that. Okay, alrighty. So that is it for today's course lecture. Homework due next before class next Tuesday. But I'm still open. If your group needs more time, just send me an email. I'm flexible on that, especially now that we have a little wiggle room before the test. Okay. All right. Everyone have a nice evening. Drive safe.
Thank you.
And I'm going to pull up the syllabus.